Hello, folks. Good morning and welcome to day 2 of the conference. Please be aware that this session will be recorded. If you'd prefer not to be recorded when asking a question, then you can send your question to the chat and it will be read out for you. I'm pleased to introduce our second keynote speaker, Diane Maclagan from the Mathematics Institute at the University of Warwick. Dr. Maclagan earned her PhD from UC Berkeley as a student of Van Stromfels. Since then, she spent time at Stanford, the Institute for Advanced Study, and Rutgers. Her research focuses on combinatorial and computational commutative algebra and algebraic geometry. And this morning's talk is entitled Tropical Geometry and Tropical Schemes. Let's all welcome Dr. Maclagan.
Okay, well, thank you. Thank you for the invitation and for the opportunity. Well, of course, it would be nicer to be in Philadelphia, but on the other hand, you probably wouldn't have dragged me across the ocean for this otherwise. So I'm going to be talking about tropical geometry and tropical schemes. And what I understand the algebra is in the title. Looking at the abstracts of the student speakers, I made a assumption that probably the weight is not close to algebraic geometry. So the hope is that the talk should be accessible without algebraic geometry. So please feel free to complain, ask questions if this is not the case. Okay, so let me start with a cartoon introduction to the talk. So I don't know which one I've shared. Are you getting does Zoom edit out its warnings, or were you getting the Zoom warnings on the screen? No, okay, good. Okay, let me start with a cartoon introduction. So this is as I said, I'll wave my hands at some algebraic geometry now, and then we'll come back and be more precise when it's relevant. The idea is that tropical geometry is a combinatorial shadow of algebraic geometry. So, and this is very cartoon, so is to say we're going to start with a variety, which is loosely the set of solutions to polynomial equations. And we're going to turn that into a combinatorial object. So this is this object on the right. So we start from X, we go to trop X, and the goal is to understand X by studying trop X. So this is a picture of an elliptic curve. So this is a tropical elliptic curve. And the sort of things you might want to understand, well, curves are, at least to an algebraic geometer, they're one-dimensional, and this is some one-dimensional object. You might know that an elliptic curve topologically is a torus. We see the shadow of that by the fact that we have a circle in this picture. And you can get more technical if you know more about elliptic curves. You might know that they're classified by the J invariant, and the length of the circle is related to the J invariant of the elliptic curve. So those are the sort of flavor of things that you might want to get out of a variety. But that's all very hand wavy and cartoony. So let me now back off. And the way I like to describe the next bit is we're going to go back to basically, I think the next probably 15 minutes is going through school mathematics from a tropical perspective. So let's start with another definition is to say tropical geometry is algebraic geometry over the tropical semiring. So I have to start by telling you what that is. So the tropical semiring is R union infinity with two operations, tropical addition, which is min, and tropical plus, which is usual. So tropical time multiplication times, which is usual addition. So that means we have things like 5 plus tropical plus 8. That's the minimum of 5 and 8. It's 5. 6 tropical times 7. 6 plus 7 is 13. So just to check everyone's on the same page, type in the chat or unmute yourself. If we have 1 plus 2 times 3 tropically, that would be any suggestions? So all of these operations are tropical operations. So the multiplication is addition. The addition is minimum.
4, correct?
Oh, I'm happier with the chat where we've got, this is the, of course we have to ask where the brackets are. So I'm assuming that we're parenthesizing in the usual way. So 2 times 3 would be 5. Minimum of 1 and 5 is who is going to be 1. So yeah, so I agree with the person who says 1 in the chat. Any questions, comments? So if you think about it now, we see that it behaves, these two operations behave a bit like usual arithmetic. So we can have 6 times 7 plus 8. This time I've put the parentheses in. 7 plus 8, that's the minimum of 7 and 8, it's 7. 6 times 7, we just decided was 13. On the other hand, if I expand it out, 6 times 7, that's 13. 6 times 8, that's 14. Minimum of 13 and 14 is 13. Okay, so you can see that multiplication distributes over addition in this way. And we have infinity is the additive identity. That means the minimum of if anything at infinity is that anything, like infinity plus 7 is 7. And 0 is the multiplicative identity. 0 times anything is that anything. 0 times 8 is 8. So infinity is playing the role of 0 in usual arithmetic, and 0 is playing the role of 1. Okay, so this means we have almost all the axioms for a ring. Okay, we have an addition, a multiplication. They're both, well, you can check they're both associative. We have distributivity. The one thing we're missing is that addition is a monoid or a semi-group, not a group. Okay, so there's no subtraction. So the problem here is a subtraction, and that means we have a semi-ring. So a semi-ring is just something that has an algebraic structure that obeys all the axioms for a ring, except for group. Addition is a monoid, not a group. Okay, questions? Okay. So I'm an algebraic geometer, so that means I want to start towards thinking about polynomials. So, but let's start with, I don't know, maybe this is 9th grade, maybe 8th grade. Someone will have to remind us when you first start to see the polynomials of one variable, and we'll actually go. So you might see something like x cubed plus x squared plus 1 times x plus 4. So in usual arithmetic, x cubed means x tropical times x tropical times x, or x plus x in usual arithmetic. So that's 3x. X squared is 2x. 1 times x is x plus 1. And so we have the minimum. This function as a function is the minimum of 3x, 2x, x plus 1, and 4. So I've drawn the graph here, and you can see it's piecewise linear. Okay, and you can see that any polynomial is going to be a piecewise linear function in this fashion, right? Because the monomials, the terms, are always going to be linear function plus coefficient. And we're taking the minimum of all of these. Okay. And then we can talk about the semi-ring of tropical polynomials, which I'll just write R bar adjoin x1 up to xn. R bar was my tropical semi-ring. And that has elements like 3 times x1 squared plus 5 times x2 plus 7. Again, all operations are tropical. So in the usual arithmetic, that is the minimum of 2x1 plus 3, x2 plus 5, and 7. Okay, and we want to think about that as the algebraic object that we're going to think about. Okay. If we want to think about roots of polynomials, so this is where you're really back in your, wherever this was, 8th grade, and you're trying to think about solving equations, this polynomial equals to 0. We run into a problem because equals 0, well, tropically that might mean equal infinity, but there's no solution to x tropical plus 3 equals infinity, right? The minimum of x and 3 is infinity, no solution. So instead, and we'll see it a bit later why this is the right definition, we divided the roots of a polynomial in one variable to be the places where f is not differentiable, okay? Or equivalently, where it's not linear, right? We said it was a piecewise linear function. We want the roots to be the place where the function is not linear. Where does that happen? It's where you get the minimum achieved at least twice. Okay, so here this is the minimum of y equals 4. We've got the minimum here is achieved at y equals 4. Here it's x plus 1. So at x equals 3, the minimum is achieved at both x plus 1 and 4. So the minimum is achieved at least twice. So in this case, we've got these 3 points where the graph is not differentiable. And that should make you at least a little happy, right? We've got a cubic polynomial and we've got 3 roots. Okay, so in this case, the roots are 0, 1, and 3. Okay, and you can check, this is an exercise to check that you have understood what the tropical operations are, that this polynomial actually factors as x plus 0 times x plus 1 times x plus 3. Okay. It involves a little bit of thought about the tropical operations. For example, what's the constant term? The constant term is 0 tropical times 1 tropical times 3. Remember, 0 is not the 0 is not the 0 of the usual arithmetic. So 0 times 1 times 3. In usual arithmetic, that's 0 plus 1 times 3 or 4. Okay, so you can check that this does factor. You might have thought, well, why didn't I just make that the definition? And that's because it doesn't quite always work. And what is true is in one variable, and this is the sort of thing where it's, it's not, you're not meant to be able to see this instantly, but if you got bored during the talk and thought about it for the rest of the hour, you might manage to prove it for yourself. It's true that every polynomial as a function factors like this, which means it's the same function as a polynomial that factors. The distinction here is that if I look at g and h as a function, this is the minimum of 2x and 0, whereas h is the minimum of 2x, x, and 0. H is x plus 0 squared, just as a polynomial. But as functions, these are the same, right? Because what functions are they? It's the function that is 2x if x is negative and 0 if x is positive. Okay, there's no place where the minimum is achieved only at x. Okay, so these are the same function, different polynomials, and one of them factors, one of them is is the product of the roots. Okay, so that's roots. So this is looking good though, right? We've got a cubic polynomial and we had 3 roots. So let's come to the next thing you learned at school, which was to come back to the quadratic formula.
Diane, I apologize for interrupting.
Right.
I don't want to make you spoil everything yet, but is there a reason that sort of tropical geometry like this would be preferable to, say, regular things? Like, is this going to be better for studying, say, those singularities, so to say?
Let's hold that question for a few slides, if that's okay.
Sure.
Yeah, we will, because hopefully I'm going to build up to that, but at least a little bit, though. I have to admit I changed this talk a lot. I didn't put as many of the obvious punchlines in this talk, but
sure.
It'll be easier to answer after in a few slides time. But I should have paused for any other questions or comments. I mean, at the moment, I haven't really told you what tropical geometry is, right? I've only told you what the tropical semi-ring is. So maybe your question is, could we have chosen a different semi-ring and done something interesting? And the answer is potentially yes. There's been less worked out, partly because the tropical semi-ring is useful enough by itself, and anything else would be more complicated. But I'll come back to that and ask again if I don't come back fast enough. But let's think about the tropical quadratic formula here. So in usual arithmetic, this is 2x plus a, x plus b, and c. So I've drawn the graph here. You can see that we have, in this case, in the way I've drawn the graph, we have 2 roots at b minus a and c minus b. Okay. You can also see, though, that this was an artifact of I made a choice about the relative size of b and the other coefficients, right? If b were large, this line would intersect somewhere up here, and then we would only have this one root, which would be c minus a over 2. Okay. So again, this should make you somewhat happy because we have a quadratic. First of all, we have a formula, just like we do in the usual case. We have 2 roots, or maybe sometimes 1 root, but that also happens in the usual case. Okay, and if you look at the equation, if you think about when do we switch from 2 to 1, when do we have only 1 root in the usual case? Okay. It's when the discriminant is 0. And if you think about the discriminant, well, we have b squared, this is tropical b squared, and we have 4ac, and this is tropical a times c. So you can see the hint of the discriminant sitting here. The other thing you should look at from this is, I mean, again, at this point, we're still just playing this game with this usual arithmetic, is you probably all know that there is a cubic formula, but if this is a, good, Anna, you're like 10 seconds ahead of me. So I'm going to pretend you didn't ask this yet, but you probably all know that there is a cubic formula. Unless you're an unusual audience, probably most of you do not actually know the cubic formula. Normally what happens, in the before times when I would give this part of an expository talk, in expository talk, I would say this and everyone would look around the room sheepishly, including distinguished mathematicians. And I'm confident that you're a very unusual audience if more than one person knows the quartic formula. Okay. However, I'm also confident that you could all work out the tropical cubic formula. You could do it during this talk if necessary. And you can see maybe here we had 2 cases, maybe you'll have 4 pieces instead of 3 for the cubic formula, and you'll get some more cases, but it's doable. And I like to think about some problems as desert island problems in the sense of, would you get, if the condition to get rescued from the desert island was solve this problem, would you get rescued? I'm confident that you would all get rescued if the condition was to come up with the tropical quartic formula. Okay, so what you should take away from this is tropical geometry is a little bit easier. To get to Anna's question, no, this is what's interesting. And so Anna's putting out that, if you've taken Galois theory recently, you know that we can't, the punchline is normally we can't solve the quintic. But here, there's nothing special, right? You can solve the quintic. Okay? So there is a quintic formula, there's a sextic formula, whatever. And remind me in 2 slides or so, I should come back to this point. Yeah, so this is somewhere where there's a slight difference. Okay, so that's the quadratic formula, and your challenge, if you check out, is come up with the cubic formula. I want to come briefly, though, to more variables, because this is sort of stock and trade of an algebraic geometer is to think about solutions to polynomials not in one variable, but in more variables. So we're going to look at first just at the tropical hypersurface. So a usual hypersurface is just, I'm looking for the set of solutions to one polynomial equation in more variables. So the tropical hypersurface, I'm just going to mimic the definition for roots. So we're going to say that the hypersurface, or the variety of f, is the set of w and r bar to the n, where f of w is infinity, or the minimum is achieved at least twice. And this bit is just for being correct, but the important bit to focus on is this minimum of f of w is achieved at least twice. This is saying the graph is not different, is not linear there. So one example is the easiest, one of the simplest examples. This is the tropical line. We might have f is x tropical plus y tropical plus 0. So that's in usual arithmetic, that's the minimum of x, y, and 0. So you might think, so I remind you, 0 is not the additive identity, so we can't remove the 0. So where is the minimum achieved at least twice? So along here, we have y equals 0 less than or equal to x. This is x equals 0 less than or equal to y, and x equals y less than or equal to 0. Then I've drawn these 2 points for this is infinity comma 0 and 0 comma infinity. So here the minimum is always at most 0. So this condition of f of w equals infinity isn't relevant for this polynomial. If we have more polynomials, so in classical algebraic geometry, of an affine variety is just the common solutions to a collection of polynomial equations. Often you package this into the ideal they generate. So I will be an ideal in my polynomial ring. And the variety is just the common solutions. So the set of x for which f of x equals 0 for all f in I. So from a tropical point of view, we're just going to define the variety of I is the common tropical solutions. So this is just the intersection of the tropical hypersurfaces for every f in the ideal. Okay, so we start with a polynomial. In the semi-ring of tropical polynomials, we get a tropical hypersurface. We start with a ideal, we get the intersection of hypersurfaces. So if I show you, this is a picture of an example with f is a polynomial of degree 2 in 3 variables. So hopefully, I don't know how clear it is from the picture. If you don't know what you're meant to see this, like it's a bunch of sheets going off, so a bunch of polyhedra. And then you've got a square here. So, and this is, if you think about this, if you're imagining a bunch of linear equations in 3 variables, you're going to get, I think, yeah, you'll get a bunch of linear things, and the minimum will be achieved twice. When 2 linear things intersect, you should get something inside a hyperplane, but then it'll be bounded off because you need it to be the minimum, not just the equality. So we get a picture a bit like this. This one is a little harder to see because I used an older software program. This is again degree 3 in 3 variables, and again you can see you've got some sheets going off to infinity and some more bounded pieces. So this is a polyhedral object in this sense. This is not so hard to see for one polynomial. So for one polynomial, I'm saying we're getting these polyhedral objects. For an ideal, you're intersecting an infinite number of things, so it's not clear that you should expect a polyhedral object. Okay. Let me now come towards answering the question and also coming back to Anna's point before. But maybe I should pause for any questions at this point, or
maybe this is not too much of a tangent, but what does an ideal look like in this semi-ring? Like, I don't know anything about semi-rings. Is this
right? Yeah, actually, I should have at least said. You've reminded me that I should have at least said the definition of an ideal is the same: closed under addition, closed under multiplication by things in the semi-ring. So, to first approximation, you could think about it as sort of looking. I mean, maybe I should ask you, what does an ideal look like in a normal polynomial ring? To first approximation, the answer is the same, right? But yeah, there is some, when you start to think about the algebra, they do play slightly different roles. I'm going to hide that slightly for this talk, but it is very related, and I'm happy to chat about it later. Okay, any other questions, comments?
Is marking the points at infinity because technically infinity is a member of the semi-ring, or is this aiming toward projective things?
So this is because infinity is the order of the semi-ring. If I wanted projective space, I would also have a point down here. So somehow, yeah, I don't. In projective space, you'd get a sort of a triangle of boundary, but it's because infinity is you should think about this as R2, and then a line at infinity and a line at infinity. And then if I want a projective space, I would have another, and the missing line to infinity would be down here. Yeah, so this is going to affine space. Some of our tropical stuff actually naturally lives in the algebraic torus. So not an affine space or projective space. Okay, let me tell you, so far I've just given you this game. I've redefined arithmetic and I've given you a game. Let me give you the connection with usual algebraic geometry. So that starts, we're going to start with a field with a valuation. So valuation is just a function from the field to R bar that behaves like tropical operations. Okay, so valuation of A times B is the valuation of A plus the valuation of B. And the valuation of A plus B is at least the minimum of the valuation of A and the valuation of B. And then valuation of A is infinity if and only if A is 0. So the first place many people see valuations is, you might have seen the p-adic valuation, particularly any number theorists will be familiar with this. If I start with K being Q and P prime, then the p-adic valuation just says pull out as many powers of P as you can. And the exponent of that, that number of P's is the valuation. So for example, if I had the 3-adic valuation of 5/6, I can pull out 3 to the minus 1. So 5/6 is 3 to the minus 1 times 5/2. And so the valuation is, that was 3 to the minus 1, it's the minus 1 I write down. So what you have to convince yourself is, if I take the product of two rationals, the biggest power of P I can pull out is the product of those powers. So the exponents add. And if I add two things, then I can pull out at least as many powers of P as the smaller, as whichever was the smallest. So we'll get at least the biggest power of P I can pull out is at least the smaller of the two, the smaller of the biggest powers of P for each of them. Somehow a tongue twister there. Okay. One thing that always works, and you feel free to think about that for the rest of the talk, is we can take the trivial valuation. So the valuation of A is 0 if A is not 0, and then it's forced to be infinity if A is 0. So that automatically obeys these two rules. And the last one, just to give you one more example, is you might take Poisson series, which is the union of Laurent series. So Laurent series, we have a power series that can have about a finite number of negative terms in T to the 1 over n for all n. So I'm allowed, basically you think of it, I'm allowed fractional exponents on my power series or my Laurent series. And then the valuation is just, I remember the smallest exponent that shows up. So again, you check, this is just properties of products of series. The smallest exponent in a product is the sum of the smallest, well, the smallest term is the product of the smallest terms. So the exponents you add, and for the addition, it's at least the minimum of the two. One nice thing about the Poisson series is that this is an algebraically closed field. So in a few slides, I'll say the words algebraically closed field, and this is just so you know one example of something where this happens. Okay. Why was I telling you about valuations? Because this lets us tropicalize. The idea of tropicalizing is I'm going to start with a usual polynomial. So I'm writing f as the sum of cu x to the u, where this is multi-index notation. So I mean x1 to the u1 times x2 to the u2 up to xn to the un. When I tropicalize, I just turn every operation into a tropical operation. So addition becomes tropical addition, multiplication becomes tropical multiplication, and then I take the valuation of coefficients, right? Because I have to turn the coefficients from something in K to something in R bar. So I start with F being the sum of cu x to the u. Trop F is now the tropical sum of the valuation of cu tropical times x to the u. Okay. And now if we start with an ideal I in the usual polynomial ring, the tropicalization of I is I just take the ideal generated by the tropicalizations of all the polynomials. You might need ideal, so again, would have to say, what do I mean by ideal generated by? In the same way as you would in the usual sense, we just take all things we can get by ideal operations. So take the smallest thing that's closed under addition and closed under scalar under multiplication by elements of the semi-ring and contains these elements. And you just to see that you might need to take the ideal generated by, if we had the trivial valuation, all these numbers might be 0. And so but I could multiply by, I could multiply by 7, which would mean add 7 to each of them. And that would be in this ideal. So just as a concrete example, if I start with 2x plus 4y plus 3, then, and k is q with the two-adic valuation, then the tropicalization of f would be two-adic valuation of 2 is 1, so 1 times x, plus two-adic valuation of 4 is 2 squared, so that's 2 times y, and then tropical plus 0, because 3 is odd, you can't pull out any powers of 2. And remember, I can't delete the 0 because 0 is not the additive identity. Okay, so I started with the usual polynomial and I get a tropical polynomial. Okay, any questions, comments at this point? So let's us get to the punchline of the introduction to the field, which is what I have told you so far is we can start with usual polynomials, we can tropicalize them. I'm going to define a tropical variety now as if I have a variety in affine space. So that was the common zeros of polynomial equations. So I is an ideal, it's a collection of polynomials. X is the common zeros of all of those polynomials. The tropicalization of X is then just, I tropicalize the ideal and I take the variety in this way I told you. So I just take the equivalently, it's the intersection of these tropical hypersurfaces, I tropicalize the polynomial, I take this locus where the minimum is achieved twice, and I intersect that. Okay, so I've combined two theorems on one slide here. The fundamental and structure theorems, we say, so there's two parts. I started by saying tropical geometry is a combinatorial shadow of algebraic geometry. The shadow comes in as follows. The tropicalization of X is, I basically just take apply the valuation to X and maybe take the closure in the Euclidean topology. So what does this mean? I've written it in the slightly more technical fashion because we have to worry about the fact that my field might not be algebraically closed and the valuation might be trivial. So what I technically do is I pass to a field extension. For example, if your field was the complex numbers, you might have passed to the Poisson series that I introduced a few slides ago. And then now your variety, it's solutions, so it's points in k to the n or maybe l to the n now. I apply the valuation. Now I've got a point in r to the n. And if I do this for every point in the variety, I get a collection of points in r to the n. I take the closure just in the usual Euclidean topology. That's some subset. And the claim is, so first of all, that's a shadow because it's just the image under the valuation. But the claim is that this shadow is the thing we got this way. So it is the object that we got by tropicalizing the equations and then taking the tropical hypersurfaces. And then where does the combinatorics come in? Well, when X is irreducible, trop X is, I'll say the sentence then interpret it. It's the support of a pure dimension of X dimensional polyhedral complex with some extra combinatorial structure. So that means every picture I've shown you so far was a union of polyhedra, right? It was this piecewise linear object union of polyhedra. The very first ones, the polyhedra were just line segments and rays. But so I've got an object here. It's a polyhedral complex, so it's a union of polyhedra, and then there is some extra combinatorial structure, which I will say a little bit on the next slide. Okay, but maybe a pause for questions or maybe the other thing I should say, well, give you a chance to catch up, is to come back to Anna's question earlier about the quintic, okay, so I said, yes, there is a tropical quintic formula. What does this theorem say about the quintic formula? This is saying, you know, if your polynomial is just your quintic polynomial, your variety is the roots of the quintic. This is saying, if I take the valuations of those roots, I get the same thing as if I tropicalize the polynomial and take the tropical roots of that tropical polynomial. Okay, so I told you that we know how to find the tropical roots of a tropical quintic polynomial. And so this is saying that we know how to find the valuation of the roots of a quintic. Okay, so we can't, there's not a nice general formula solving the quintic and radicals, but we can, if you have any valuation, maybe you've extended one of your p-adic valuations on Q, we can find the valuations of the roots. So it's one of those things that we somehow, because Galois theory is so beautiful, we tend to get, oh, you can't solve the quintic. And we're forgetting that, well, you know, of course, if you give it to a numerical root finder, you can. But even if you'd like to stay outside numerical matters, we still can. There are still, you know, much more information we can get about this in this way. Okay, any other sort of questions or? Maybe we say, when I said there's extra combinatorial structure, what we mean is, if you've seen any tropical talk before, you might have seen people talk about the balancing condition or the zero tension condition. And this means if these aren't arbitrary polyhedra, they're arranged in such a way that if I did played tug of war, I stood here, 3 people have ropes, they pull with equal strength, or sometimes you put weights and then they pull with those strengths, and no one wins, right? If you made the structure out of some metal, it would be at zero tension, it wouldn't pull itself apart. And to come back to the question of why do we make the definition, which came earlier, why do we make the definitions in this fashion? Again, the goal was to understand X from trop X. So some examples that have been successful in the past are, so the Gromov-Witten invariance of P2, this was Grisham Maclagan's original work that's kind of started tropical geometry 20 years ago. There's been a lot of work on Brill-Noether theory, tropical Brill-Noether theory, particularly Sam Payne, Dave Jensen, and I guess Jan Dreismer, and a bunch of collaborators. More recently, cohomology of MGN of moduli space is by particularly Melody Chan, Sam Payne, Soren Glacius, and again, collaborators. And so these are just some of the highlights. And these last two use a slightly different presentation of tropical geometry than the version I've given you, but it is related. But this first one really is drawing pictures like this and seeing where we go with that. Okay. So that's an introduction to, you know, what tropical geometry is. With the rest of my time, I want to tell you a little bit about what we've been doing recently. But if anyone wanted to interrupt with questions at this point, that would also be a good point. Okay. So maybe at this point we do take it up slightly a notch, but I'll try and again keep it accessible to outsiders. If you're not an algebraic geometer, the one thing that you've probably picked up about algebraic geometry is that it changed rather drastically in the 60s. So the story I've been telling you so far, where I've just said varieties, common solutions to polynomial equations, is something that a 19th century algebraic geometer would recognize. So in the 60s, Grothendieck introduced the theory of schemes. Roughly, I mean, there's many reasons why you might want to suddenly think about schemes, but it gives you a way to talk about algebraic geometry over arbitrary rings and fields. So to think of number theory as part of algebraic geometry, and to also think about things like, what does it mean to say we have fat lines and things like this. For the purposes of this talk, all you need to know is affine schemes. So it's really commutative algebra. That means we're really going to think about ideals in the polynomial ring. So a subscheme of affine space is an ideal, corresponds to an ideal in a polynomial ring. So people who know some algebraic geometry will know that means I'm saying X is the spec of the quotient of the polynomial ring by the ideal. So naively, at this point, you're meant to think, well, we kind of know affine space is just k to the n. I can tropicalize that, I get r bar to the n. I know how to tropicalize polynomials, I get tropical polynomials. I know how to tropicalize ideals, I just tropicalize. Multiplication turns into tropical multiplication, addition turns into tropical addition, take the valuation of coefficients. So naively, you'd think, well, we know how to tropicalize this. We should just turn and yeah, we should just tropicalize the ideal. There are some problems though. Okay, the first is every picture I've drawn you so far, and I said that this would in the structure theorem, the point was that we were getting polyhedra. But if I take an arbitrary ideal in the semi-ring of tropical polynomials, the variety can be fairly arbitrary. So in particular, we can get something like a disk, maybe with some lines, in particular, not a finite polyhedral complex, so not a finite union of polyhedra. Okay, so that's one problem, and that's a problem from my perspective. Everything that's made tropical geometry successful over the last 20 years, I think, has hinged on the fact that we've turned these hard algebraic geometry problems into still sometimes hard, but at least more tractable polyhedral combinatorics problems. And so if you don't turn it into a combinatorial problem, you're at least at best you're in a different field, and you're throwing away most of the tools that have been successful. So that's a problem. Another issue is that the semi-ring of tropical polynomials is not Noetherian. Okay, so there are ideals that are not finitely generated. Okay, if you've had, many of you probably learned Noetherian in maybe even your first algebra class. If you've had a commutative algebra class, you will know that Noetherian rings are the rings we like normally. Okay, so we run into trouble right at the start for one of the simplest ideals you can think about. If I just take the principal ideal generated by x minus y, when I tropicalize, x minus y turns into x tropical plus y. But we also have x squared plus y squared in the ideal, okay? Because that's the tropicalization of x squared minus y squared, which I didn't tell you what the field was here, but it doesn't matter, right? It's still going to be here. And then you can see we'll get x cubed plus y cubed, because x cubed minus y cubed is also a multiple of x minus y. And here's where we get a problem, right? X squared plus y squared is not a tropical multiple of x plus y. Okay? Any multiple you have, if it's going to contain an x squared, it'll have to be x plus y times x plus something, but then we'll get an xy term, and because there's no subtraction in the tropical semi-ring, we can't get rid of it. So here we have, we definitely need x plus y as a generator, but we also need x squared plus y squared. And it's not too hard to convince yourself that we really need all of these things. So this is an infinitely generated ideal. We started with a nice, simple principal ideal, and we end up with an infinitely generated ideal when we tropicalize. This is unfortunately something that we have to just live with. But I'll give you a little bit of the hint of how we're going to get around it. So the solution that, this is coming from work of mine with Felipe Rincon, who's at Queen Mary in London, based on work of Jeff and Noah Jedzer and Cusa. We're going to restrict the class of ideals we're allowed. Instead of saying, okay, I said, if you take the variety of an arbitrary ideal, we look like something that doesn't belong in this subject. So I'm going to say, don't take the class of all ideals. So I'm going to define a tropical ideal now. This is going to be an ideal in the semi-ring of tropical polynomials that satisfies an extra condition. And this extra condition is a way to artificially put back subtraction. Okay, the problem with the tropical semi-ring is that we don't have subtraction. And so we're going to artificially put back subtraction in the following fashion. Okay? We're going to say whenever we have two polynomials that have the same coefficient for some monomial x to the u. So this is my notation for the coefficient of x to the u in my polynomial f. So if f and g have the same coefficient of x to the u, then I'm going to say that there has to be an h also in the ideal where that coefficient is infinity. And then there's a condition that the other coefficients are at least the minimum and actually have to be equal to the minimum if these two numbers are different. Okay, where does this come from? Why is this a good definition? Let's think about the cases when I is the tropicalization of an ideal J. Remember, we said one way to get an ideal in the semi-ring of tropical polynomials is to start with an ideal and then for every polynomial in the ideal, just tropicalize that, take the ideal generated by that. So in that case, if little f and little g might be the tropicalizations of capital F and capital G, you can choose capital F and capital G by multiplying by something of valuation 0, so that if these valuations are the same, so if we have the two-adic valuation, that would be saying you can pull out the same power of 2, and then we can make actually the coefficients of x to the u and f and g the same. If I have two usual polynomials where the coefficients of, say, x squared y are the same, and I want to get one where that coefficient is 0, well, a good way is just to take the difference. So in this case, h is just the tropicalization of f minus g. So that will give me a polynomial where the coefficient of x to the u is now 0 in capital F minus capital G, so it's infinity in little h. And then this condition is just the condition on valuations, because the valuation for x to the v, the coefficient of x to the v is the coefficient in f minus the coefficient of g, and this is the condition on valuations in a sum or a difference. Okay. And I'll just make a side remark for anyone who likes combinatorics and matroids, that this is secretly a matroid condition. Okay. But at the moment, what have we done? We've given a definition of a tropical ideal. It's not too hard to come up with examples to show that not every ideal in the semi-ring of tropical polynomials satisfies this condition, but every ideal that arises as the tropicalization of an actual ideal does satisfy it. So we've got a fairly simple way to give an extra condition, and it's artificially putting back subtraction. So that lets us define in a tropical subscheme of tropical affine space to be just defined by a tropical ideal. And for the experts, I mean, again, we've tropicalized this, and then we have to think about what to do. So maybe I won't say anything about this, though feel free to ask later. So this is where work of the Jen Syracuse brothers comes in. And let me just we'll finish the main part by saying I'll give you a cartoon version of our theorem. This is work with Felipe Rincon to say if we put this extra tropical ideal condition in, then varieties of tropical ideals behave like tropicalizations of varieties. Okay? And that means we can build a theory of tropical schemes with them. So you somehow, so that's the cartoon version. Maybe I'll just put up, but perhaps we won't go through in detail since we have time to leave us time for questions. And there are, maybe I'll highlight this piece. We have the varieties of tropical ideals are finite polyhedral complexes of the same dimension as the dimension of the ideal. Oh, and the maximum dimensional strata is balanced, meaning it satisfies this combinatorial condition that I hinted at in the structure theorem. So that's one way in which we have varieties behave like tropical ideals. So this is the technical, so I won't go through all pieces of this, having given you the cartoon version. But the other one is I said tropical ideals are not Noetherian. so semi-ring of tropical polynomials is not Noetherian, but it turns out tropical ideals do obey the ascending chain condition, which is, you might remember, is one part of the definition of Noetherian. So what that means is there doesn't exist an ascending chain of tropical ideals. If you've thought about Noetherianness recently, you might be confused because it's purely formal, the connection between the ascending chain condition and ideals being infinitely generated. So what this means is there can be an infinite ascending chain of ideals, but only finitely many of them will ever be actually tropical ideals. And then you can see we have a bunch of other conditions, other facts, which are just justifying this cartoon version of the ideals. If you start with a tropical ideal, you get a theory like the usual one. And that's what we want to build our tropical scheme theory around. So maybe that's a good place to stop so we have time for some questions.
All right, let's all thank our speaker. And if anyone has any questions, feel free to speak up.
I have a question. And it may be like a question that has no answer, or I don't know, or if it just doesn't make sense in tropical geometry sense. But so for instance, you know how in regular geometry, normal geometry, if I have, let's say, a curve, I can take a point in that curve and consider the tangent line to that algebraic thing. Is there such a thing for tropical geometry? Like if I have a tropical variety that you connect.
Sort of, that's a complicated, it's a good question, and the answer is surprisingly complicated. So, and I think it's surprisingly complicated in a way that means we don't yet have quite the right answers. You can still talk. I mean, one way to define a tangent line to a curve is to say, well, it's going to intersect, and it's going to intersect with multiplicity 2 in a nice way. And you could define multiplicity of intersection. That's something that works well in tropical geometry. So there's a combinatorial definition of that. But when you start thinking about tangents, life becomes a bit easier. So a bit more complicated. So something people have spent actually quite a bit of time thinking about tropicalizing a lot of the beautiful 19th century theorems about plane curves. I mean, one example would be, one example that's I think been thought about very recent in the last year or two is if you take a plane quartic curve, it has exactly 28 bitangents classically. If you have a smooth plane quartic curve, classically it will have exactly 28 bitangents. That means lines that are tangent in exactly 2 points on the curve. And if you try and draw this tropically, what happens is you might get more than one. There might not be exactly 28, but there are somehow 28 in, sorry, actually, well, it's not 28. You end up with 7 because they come, and I think it is, as long as I'm remembering this correctly. This is work of, I guess, Hanna Markvig, Jov, Len, I think Angie Cueto's involved somewhere, and a bunch of other people, but they cover these equivalence classes somehow. And so you do get a shadow. What I would like actually with this new work of thinking about schemes is to define tangent. I mean, instead of thinking of a tangent line just as a variety thing, to sort of develop a tangent space in the way that we think of it as a risky tangent space and make some sense of that. But we haven't yet. I mean, yeah, it's kind of works in theory, but we haven't yet been able to actually get any applications to algebraic geometry problems from that.
And what about, like, let's say something like duality, like this, a way of relating lines with points?
Yeah, that's a very nice question. Again, so Jov, Len, and Nathan Milton have one paper about this. So one question you might ask is, so if I have a curve in the plane, right, so there's 2 things. There's the first, there's just the points versus lines in duality. If you have a plane curve, you can take the, as maybe for other people, you can take the dual curve, which is You
Yep.
take the collections of tangents at smooth curves, and sorry, at smooth points, and that gives you the dual curve. One of the things that's always weird when you first learn about that, is that you first get is if you start with a curve of degree d, the dual curve has degree d times d plus 1 in general, but it's still a duality, and so that's one of these weird things. So Nathan Milton and Yoav Len can tell you the question: if I give you the if I give them the tropicalization of my curve, so the pictures I was drawing, they can give me back the tropicalization of the dual curve as long as the curve is generic enough. And then there's also, this is something that I've also thought a little bit about with Polina Mincheva, of trying to understand this from a more scheme theoretic point of view. So there's some work on it, but we don't, I mean, we're still at the stage for some of these things of just for some of these things of really trying to deeply understand even some of the things were classical 19th century questions.
Okay, great. Thank you so much.
Can I ask a quick question, Doctor? Can we consider the lattice? I noticed the order structure of the semi-ring. So can we consider the lattice structure about it? If we can, so what's the difference if we use the lattice ring instead of the semi?
So by the lattice, sorry, what by lattice structure do you mean? Are you thinking about lattice do you mean lattice as in the group sense or the poset sense?
A group sense.
Okay, so do you mean, like, for example, think about the z to the n inside r to the n? Is that? I'm just saying. So that's definitely. I mean, so secretly, everything. Maybe, well, one answer is everything I said for affine space. It was secretly everything secretly held for toric varieties, which there we go to we spend a lot of time thinking about the lattice inside polyhedral objects. So, and I mean, the answer is, from assuming that we're talking about the same lattice, then the answer is yes. The fact that we have a lattice structure, and when I said polyhedra, these were really always what I call R-bar rational polyhedra, meaning their normal vectors were always rational. So everything inside has a lattice structure.
Okay, thank you for your answer.
Anything else?
All right, if there are no other questions, let's thank Dr. Maclagan again. And now we have a coffee break that will be in the Gather Town. The next student session will start in 20 minutes.